Thank you very much for the introduction, and thank you very much to the organizers for giving me the chance to present my talk here in this conference. Let me just, okay. Okay, so my talk will be about approaches to set optimization in real linear spaces without convexity assumptions. This is the content of my talk. So at first I would like to talk about an introduction to set optimization, where is set optimization used, and what is the general problem formulation. After that, I will introduce a generalized set relation that is derived from a very well-known set relation, and I will give an equivalent representation of this set relation in terms of nonlinear scalarizing functionals. In a third part of the talk, I will extend the solution concept to approximate solutions and give some results that we obtained there in real linear spaces where we do not assume any topology. And in the end, I will give some references.
Sorry, Elisabeth, we are not seeing any
slides. Sorry.
Only your first slide.
Oh, okay.
I think we had this issue in the morning as well. Are you using Mac?
Yes. Can you see now the second slide?
Yes.
Yeah, now it works.
Yeah. Okay.
Then I will keep it like that. I had it in full screen mode, but probably the problem was in full screen, it does not work. So now if you see it, it's fine.
Someone mentioned in the morning that full screen doesn't want to work with Mac computers, but maybe it was a hypothesis.
Okay, yeah, well, maybe it's true because now I'm also using a Mac and it's the same problem. Okay, so now I will continue in this way. Okay, so now considering the motivation of considering set optimization problems. In a paper from 2017, together with some co-authors, we considered the optimal layout of photovoltaic power plants, where we actually had two objectives. We wanted to place the power plants in a way such that the energy output would be maximized and the associated costs would be minimized. And this would give us a B criteria optimization problem, so an optimization problem with two objective functions. And we had some uncertainties, namely the weather data providers. So we were collaborating with Siemens, and Siemens had three different weather data providers that would supply us with their weather data in order to, so we could use this to compute the energy output and the associated costs. And because there were multiple weather data providers, these would give us different values of the energy and the costs, which then led to three different points in the objective space. And we considered this as a set optimization problem. And this is an example of how uncertainties in the objective function can lead to a set optimization problem. And here we had actually 14 different layouts of photovoltaic power plants that we considered. And we were able to classify robust solutions. That means kind of optimal allocations of these power plants that were working well in the worst case scenario. And we were also able to consider optimistic solutions, and this means layouts that work well even if the best case scenario happens. What I mean by uncertainties in the objective function, I want to specify this in the following way. Let's assume that we have a scalar valued function f. Here is the x-axis, and let's assume that if the function is given, then we have fixed function values for each x, and we have a fixed function. However, if there are some uncertainties in the objective function, it's possible that we get different function values. For example, these red dots here, then we would get a different function. And this can happen for, of course, many values. And then what we end up with is actually a set valued problem. So we are considering for these each points x all set in the outcome space here. And this leads us to a set valued mapping, which is here in this talk denoted by capital F. And capital F then is just the allocation of all function values f overall xi, where xi is the so-called uncertain variable, and xi belongs to a predefined uncertainty set here. For a B criteria optimization problem, this looks the following way. So we have two objective functions, f1 and f2. And let's say the function, the objective function is fixed. We have no uncertainties. Then for each point x, we get 1 point in the objective space. And we are interested in this Pareto frontier, which is made up by the blue dots here, by the blue stars. However, if there are some uncertainties, it's possible that these points are not really defined properly. There may be different function values that are obtained. So then we are left with something that could look like this. And here we are also interested in something that looks like a Pareto frontier. Okay, so now to the mathematical problem formulation. We assume that we have two linear spaces given that are x and y. By P of y, we denote the power set of y without the empty set. And F is the set valued mapping. That is our objective mapping. It maps from a subset S of the space X to Y. And this is the mapping that we want to minimize. And the problem then reads as follows. We want to minimize F on the set S. We call this problem P in the following. This is the set valued problem. So now, of course, because we are working in the power set of Y, we do not have a total order. So now we need to define what optimality means in this case. So the question is, how are minimal solutions of this above problem defined? And the idea is to compare sets by means of set relations. And these set relations are given by this notation here. And then minimal solutions are defined as follows. We say that an element x bar, which is in the feasible set S, that this is a solution of this problem P if for all other x or for all x in S, this implication holds. This means that if we have an x that is better or equal than some f of x bar, then it follows that f of x bar is better or equal than f of x. For these set relations, there is one set relation that is well known in the literature by Daishiko Iba. And this is given in the following way. Let's say that we have a set D that is a convex cone. And then this upper setless relation, this is notated by this sign here, is defined for two sets A and B in the following way. A is better than B if A is a subset of B minus D. And by this relation, we are able to, for example, check whether this set A is better than a set B in a robustness sense. And by robustness, I mean that in case we have an uncertain objective function, then these sets here, A and B, would kind of represent all the possible values that can happen in the objective space. And the worst possible values would then be, because we have a minimization problem, would then be allocated here in this above border here, and in the boundary above here. And because if we have B minus D, we are kind of comparing these sets by means of their upper bounds. And this corresponds exactly to the idea of robust optimization. So here we have that A is better than B because A is a subset of B minus D, where D is the natural ordering cone in R2. Here, A is not better than B, but here A is again better than B because these worst cases here are not dominated by these worst cases here. So now what we've done is we have generalized this definition, and now we assume that D is not necessarily a convex cone anymore, but just a non-empty set. And then this we define the set relation in the same way as before. And the advantage that we get here is that we get, again, we can use D as the natural ordering cone in R2 again. So we get the same definition as before. However, we can also model, for example, set inclusions. We can model that A is a subset of B minus D, where D is the just the zero vector. Or here, if D is just one non-zero vector, we can model relocations of a set or subsets of relocations of a set. Some properties concerning the set relation. We can note that the set relation is transitive if this relation here holds. That means if D plus D is a subset of D. If D is a cone, then this relation implies that D is convex. So for example, if we choose D as the natural ordering cone without the zero vector, then this relation here is fulfilled, but D is not a cone. Moreover, we have that this relation is reflexive if zero belongs to the set D, and therefore we can conclude that this relation is a pre-order if this relation here, this inclusion is fulfilled and zero belongs to D. Okay, now our goal is to characterize this set relation in terms of nonlinear scalarizing functionals in real linear spaces where we do not assume a topology. And for this, we need to define the vector closure of a set, of a given set. So let's assume that we have a set F in the objective space Y. Then the vector closure is this set. This is the set of all Y such that there exists a V in the objective space Y such that for all lambda that are bigger than 0, there exists a lambda prime in this interval here, such that Y plus lambda prime multiplied by V is again in F. And this is called the vector closure of F. If we have given a vector K in Y, then we also define the vector closure of F with respect to this vector F, which is given in this definition. So this is the set of all Y such that for all lambda bigger than 0, there exists a lambda prime in this interval here, such that Y plus lambda prime multiplied by K is again in F. Furthermore, we say that F is K vectorially closed if the vector closure of F with respect to K is F itself. And F is vectorially closed if the vector closure of F coincides with F. Obviously, it holds that by the definition that F is a subset of the vector closure of F with respect to K for all K. This is a relation that we will use in the following as well. Now, the nonlinear scalarizing functional that we want to use is the following. This was first given by Christiane Tammer in the 80s, and we call this functional Z, and the parameters are D and K. So again, Y is a real linear space, D is a non-empty set in Y, and K is a non-zero vector in Y. Then we define this function as the following. It depends on Y, and it assigns the smallest possible value T in R such that Y is an element of TK minus D. However, if Y does not belong to RK minus D, then this function value is just assigned as plus infinity. So if you want to have a look at the picture, which is maybe a little bit easier to see, here we have D as the natural ordering cone in R2, so this set here. K is a vector in D here, and this is Y. And then our functional here defines the smallest value T such that Y actually belongs to TK minus this natural ordering cone here, as you can see in the illustration. We will use the following important properties of this functional, which are found in a paper by Gutierrez and his co-authors. So here D and E are non-empty subsets of Y, and K again is a non-zero vector. Then we have this property. The function value of Z is bigger or equal than 0 if and only if Y is in this set here, where here we have that the 0 can be obtained here. And we have that the objective function value of Z is strictly smaller than 0 if this holds, where here 0 is excluded from this interval. Furthermore, we have that Z is E-monotone if and only if this inclusion here holds true. And we have the following property. We have that for all Y and real values R, Z of Y plus RK is equal to Z of Y plus R. Okay, so in case we have a finite dimensional space Y, let's say Rn, and D is given as a polyhedral ordering cone, and K is in the interior of D, then the function value Z can be easily computed as this value here. And this can also be easily implemented. We've implemented it in MATLAB. So this is just to show that it's a very useful functional for our purposes, and we can easily use it. So now our goal was to use this functional in order to represent set relations, in particular the upper setless relation, as I've introduced before. And now the first theorem that we have is the following. Assume that D is a convex cone. Then we have that if A is better than B with respect to this upper setless relation, then this relation here holds true, this inequality. The proof is very short because we've assumed that D is a convex cone. This relation here, this inclusion holds true. We know that D is always a subset of the vector closure of D with respect to K. Now we can say that this is equal to just a zero vector plus the vector closure. And then this inclusion here also holds true. And now we can use one of the properties proved by Gutierrez, which was property C. It is written again here. We need the demonotonicity of Z, and this is exactly what we have proved now. Now assume that this set relation here holds true, and this means that A is a subset of B minus D. Then for all A, there exists a B such that A is an element of B minus D. And using the demonotonicity that we've just proven, this immediately yields the result. So this is again the same theorem here, and this is just to show that the reverse implication does not hold even if the sets are convex. So for example, if we have here A as a single valued set, which is just 1 point, and B minus D, or B is this set here, the red line, and B minus D, where D is the natural ordering cone and R2 is just this convex set here, then obviously we have that A is not a subset of B minus D. However, this part here is fulfilled because we have the supremum of Z over B. If we include this set B here, then we get that this is the supremum of the maximal value of S over K1 and 1 minus S over K2, where K is assumed to be in the interior of the ordering cone in R2, of the natural ordering cone. And then this is equal to the maximal value of 1 over K1 and 1 over K2. So if we assume that both K1 and K2 are bigger than 0, which is what we assumed because K is in D, in the interior of D, then this value here is bigger than 0. And for the first part here in this inequality, for the supremum of Z of A, we have that A is just 1 point, so we can just write Z of A. This can be calculated as the point that was given, which was in our case 3 over 4 in both dimensions. So this is just 3 over 4 multiplied by this value that we obtained above here. And of course, because this is bigger than 0, this is then this value here is then strictly smaller than this value above. So this is fulfilled. This shows that the inverse of the theorem is not fulfilled. However, we have the following theorem. We have that if A is better than B, then this inequality here holds true. And on the other hand, if we assume that there exists a K0 such that this inner value here of this inequality here is attained for all A, and D is K0 vectorially closed, and this inclusion here holds, then the inverse implication also holds. That means that if this is fulfilled, then A is better than B. So for the proof, let's assume that A is a subset of B minus D. This corresponds to this assertion here. And of course, we know that minus D is a subset of minus the vectorial closure of D with respect to K. Now we can use property A from the theorem concerning the nonlinear scalarizing functional. This is given again here. So this immediately yields that for all A, there exists a B such that this inequality holds true. And this exactly gives us our first assertion, which was that this inequality here holds true. Now for the inverse direction, we assume that this here is fulfilled. And this means that for all a, we have that the infimum here of this function value is smaller or equal than 0. Because we had assumed that for all a, this infimum here is attained, we obtain that for all a, there exists a b overline b, such that this value here is equal to the infimum, which is smaller or equal than 0. And this immediately implies by using again by using property A, that for all A there exists an overline B such that this point here is included in this value here, in this set. And therefore, by rearranging the terms, we can see that A is a subset of B plus this value here. And this is a subset of B minus D according to our assumption, which was given here in this assumption of the theorem. Okay, the following example then shows that the attainment property in the preceding theorem cannot be omitted. So for example, if we have that A is just 0 vector, just a single valued set, and B is this square here, which is open, D is R2 plus, and K0 is the vector 1, 1. Then we have that the vector closure of D with respect to K0 is just D, and this inclusion here holds true. So all the other assumptions in our theorem are fulfilled. And it does hold that this is smaller or equal than 0. However, obviously, A is not a subset of B minus D. And this is because this inner value here, the infimum, is not attained for the specific value of A. However, we have the following theorem where we can omit the attainment property. We have that if this inclusion here, as well as this inclusion, is fulfilled, then we have that this inequality implies the validity of the set relation. Perhaps due to time, I will skip over the proof. And now just some concluding remarks concerning this part. We have derived according characterizations for other set relations as well. And the representation of the set relation has been used to develop a new set relation that can be kind of regarded as a weighting between two prominent set relations. This means between the upper and the lower set relation. So we've included this set relation, which we called weighted set relation. So here we have said that A is better than a set B if some parameter lambda multiplied by this value, and this is just the value that was given in our theory, plus 1 minus lambda multiplied by this value. Now this here it looks similar, but the roles of the suprema and infima are just reversed in order to get a different set relation, the so-called lower set relation, which is associated with optimistic solutions of uncertain optimization problems. So if this whole value here is smaller or equal than 0, then we say that A is better than B. So our representation was used for deriving new set relations as well. And now it is very well known that optimal solutions of optimization problems do not always exist. And therefore, it's important to consider approximate solutions as well. And this is what we have done in a work with Gutierrez, Huerga, and Tama. So here we said that X bar is, for example, an H1 approximate minimal solution of the original problem if for all X, if this is fulfilled, then f of x should be better than f of x plus h. So here this h is on the right-hand side here, but here it does not appear. And we have also defined a different definition for approximate minimal solutions in this way, which we called H2 approximate minimal solutions, where we say that if f of x plus h, and here this h appears here on this side as well, if this set is better than f of x bar, then f of x bar is better than f of x plus h. So for certain assumptions concerning the ordering cone D and H, we get that the set of minimal solutions is included in the set of H1 minimal solutions, and this set is then again included in the set of H2 minimal solutions. So for single valued sets, we get, for example, this example here. These are the minimal solutions. And here we have the H1 minimal solutions, and here are the H2 minimal solutions. And for set-valued mappings, which are non-convex, here we have an example. We have calculated the minimal solutions, which are here given in this. These are the blue ones. Here, these are the H1 minimal solutions, and these are the H2 minimal solutions. And in our work with our co-authors, we have defined an inequality approach in order to find these H1 and H2 minimal solutions in terms of inequalities. So I see that I'm well over time. So maybe should I skip this part?
Yes, please.
Okay, yeah, okay. So I will just skip this, and I will just say that we then derived here inequalities, and we found we found equivalent representations of H1 and H2 approximate minimal solutions just in terms of single valued inequalities. Okay, and now just some conclusions. We have now given novel directions in the optimization process of set-valued mappings that are not necessarily convex, and why being a real linear space where we did not assume any topology. We have extended our set relations and their characterizations by means of nonlinear functional, and we've given new notions of approximate solutions for set optimization problems and representation by an inequality approach. So these are my references. So the papers that I talked about today were this one for the first part, together with Niklas Hebestreit, and the second paper was this one, an inequality approach to approximate solutions of set optimization problems in real linear spaces. Okay, thank you very much.
Thank you, Elisabeth. Any question from the audience? So we have time for 1 or 2 questions.
Can I ask a question?
Okay, please.
First, thank you very much for the very interesting presentation. So the quantity that you defined that involved is sup inf z d. Typically, for which kind of cones would I be able to compute these kind of things? So sorry, it's a bit of a vague question, but I'm just curious about how hard is to compute these things.
Yeah, yeah, that's a good question. Let me just go to the slide. So you mean like a representation of this kind here?
Yes, yes.
Mm-hmm. So in our papers, we have done this where D is a polyhedral ordering cone, and K is just included in the interior of D, and we are in of course, in a finite dimensional space. Then this can be easily computed, this value. We have not done any calculations for infinite dimensional spaces.
But for example, even for finite dimensional case, how about if, say, the cone is, say, the second order cone, or some cone, or when a space of matrices, say the positive, and this is the positive semi-definite matrices, something like that. So more complicated wood than polyhedral, but still with some structure.
What do you mean? What kind of cones other than polyhedral cones? This is what you mean?
Yeah, yeah. So for example, also I see that Vera is. So should I stop?
Yeah, Bruno, I just have a comment on your question. Are you thinking of using Jordan algebras here?
No, not necessarily, not necessarily, but just yeah, some kind of thing that.
Did you might?
Yep.
Yeah, Elisabeth, just Bruno gave a talk on Jordan algebras earlier, so I'm thinking he's probably trying to use Jordan algebras and symmetric cones.
Oh, sorry.
Okay.
No, that's just the first thing that comes to my mind. But yeah, what I wanted to ask more generally was, how about for some nonlinear or non-polyhedral cone, are you able to get some, even in finite dimensional space?
Yeah, I cannot answer this correctly because I'm not sure about that. It depends on the cone itself, and whether it can be easily evaluated using this functional. So we have evaluated this functional for the natural ordering cone in finite dimensions for polyhedral ordering cones. Yeah, I think, and that was it for our examples. But of course, it would be interesting to check other formulations of D and see whether this can be easily computed.
Okay, thank you very much. Cool.
Thank you.
You may want to try symmetric cones. They are cool.
Okay.
Thank Elisabeth for your talk.